Hello, welcome to session number 2 in the series Engineering Mathematics. My name is Anurag Nigam, and as mentioned in the uh, previous session, I'm going to take up matrices this time. So the singular is matrix. Just one second, and its plural is going to be called matrices. And then you have a software called MATLAB, which is a matrix laboratory, and this MATLAB basically inside it's based on uh, a library which is called LAPEC. Okay, and this calls most of its function from something called BLAS. So BLAS stands for Basic Linear Algebra System, and LAPEC has to do with linear algebra, right? And in between there was something called LinPack, right? So LinPack was optimized into LAPEC, so you can basically download these libraries which are accessible through C. They are also accessible through C#, right? And most of the engineering softwares are using this for most of the matrix manipulation, right? So including MATLAB. And there is something called TNT also, and that TNT is another library similar to LAPEC. It uses LAPEC and BLAS, right? And this effort, is a research. I think it's by MIT. Yeah, it's MIT, I think, and sponsored by MathWorks and Intel. So what we are going to do is later on we are going to configure a system using LAPEC, and we will be able to do all matrix manipulation in C. But meanwhile, okay, what we are going to do is we are going to start with very basics of what is a matrix. So matrix is a two-dimensional array. So matrix is two-dimensional array. So that means that it has got certain rows and certain columns. For example, let's put a matrix here: 2, 3, 4, 5, 6, 7, 8, 9, 10, let's say. So this is a matrix. Now the members or the entries of a matrix can be a complex number also. So there is no restriction on what these entries can be, right? So it has got, right now you can see it has a two-dimensional matrix. It has got 3 rows, right? Row 1 to row 2, or rather row 0 to row 0, row 1, and row 2. Okay, and then it has got, sorry about that, it has got columns, right? So you have got column 1, column 0, column 1, and column 2, right? So a matrix is a array of a two-dimensional array of numbers. Now matrix can be more than 2 dimensions, right? So first thing first is, what is the order of a matrix? So order of matrix is its dimensionality, right? So I can say a matrix is a 3 by 3 matrix. So that would be the order of a matrix. Now a matrix can also be made up of rows. Okay, now these rows, they over here, for example, all these rows are linearly independent. So what it means is that none of the rows can be expressed as a algebraic sum of two or more other rows, right? So if you cannot express a row as an algebraic sum of 2 or more rows, then that matrix, basically the what you call the rank of the matrix, in that case is the dimensionality. So what it means is, so for example here you see that the rank of the matrix is 3, because neither of the rows can be expressed as an algebraic sum of other rows, right? So having said that, there is something called the rank of the matrix, right? So rank is basically rank of a matrix is the number of linearly independent rows or columns of a matrix. That's called the rank of the matrix, right? So where do these matrices show up, right? So for example, let's say we have got x1, x2, these variables are there up to, let's say, xn, right? So I can have for these n variables, they can satisfy n system of linear equations. So I can say a1 1 x1 plus a12 x2 plus a13 x3 plus and so on up to a1n xn is equal to b1. So let's say this is a linear equation. What do you mean by linear? None of the variables basically have order other than 1. So it is not a square, it is not a square root, right? It is not a multiplication of two variables. So you will not find a term where you have x1 into x2 or x1 into x3, or you will not find a term x1 square or x2 square. Okay, so linear equation is the one in which the order of a variable is 1, nothing other than 1. The coefficients can be 0, right? But then there is no way that the order is going to be other than 1. So that is called a linear equation. Now, if I have a system of such equations, so I can have a2 1 x1 plus a2 2 x2 plus a21 x2, sorry, let me not mess this up. Okay, a22 x2 plus a23 x3 plus and so on plus a2n xn is equal to b2. So similarly, I can have n such equations. So if there are n variables, I can have n such equations where it will be an1 x1 plus an2 x2 plus an3 x3 plus and so on up to ann xn bn. Okay, so now this system of equations is a linear system of equations, right? Now a matrix can be a coefficient matrix. So for example, I can say all these terms which has 1 1 1 2 1 3 and so on up to 1n, and then 2 1 2 2 2 3 up to 2 a2n, and then going down up to an1 an2 an3 and so on up to ann, right? So now this matrix multiplied by x1 x2 x3 and so on up to xn is equal to b1 b2 b3 and so on up to bn. So a linear system of equations can be expressed as matrices, as a coefficient matrix multiplied by the variable column matrix equal to the right hand side, which is numbers, right? Now if this right hand side, which is b, is all 0, so if this b is all 0, then that means that this is a homogeneous linear equation, right? So that would be, if b is 0, then this is called homogeneous linear system of equations. Now why do we study matrices? So first application is right in front of you. So if I have got n variables x1 to xn, and I have n such equations, I'll be able to find the solution for this equation, and the solution for this equation is going to be this vector x1 to xn. These are the variables, right? So there is a matrix of these variables which satisfies this system of equations, right? Okay, so So that's one of the applications of matrices, right? To be able to solve system of equations. Now little bit about consistency. So what happens is, let's say all these rows of this coefficient matrix, okay, all these rows of this coefficient matrix, they are linearly independent. That is, none of the rows can be expressed as an algebraic sum of or weighted sum of other rows, right? Then this rank of the matrix would be n, right? So for this n by n matrix, if all the row entries, or you can say all the column entries are linearly independent, then the rank of this matrix would be n, right? So for to be able to solve this system of equations, the rank of the coefficient matrix should be n, same as the dimension of the matrix, right? Then only you have a unique solution. And another thing which you are going to have is there's something called an augmented matrix. Okay, so what is an augmented matrix? I can put a11, a12, a13, and so on up to a1n, and then I can have 21, a22, a23, and so on up to a2n, and then similarly I can continue and I have an1, an2, an3, and so on up to ann. So this is a coefficient matrix. So if I add another column to it, which is b1, b2, b3, and so on up to bn, okay, so this matrix would be known as augmented matrix. Okay, for short I can put this. So this is an augmented matrix. Now in this case, if the rank of the matrix, coefficient matrix, okay, rank of this coefficient matrix, sorry about that. Okay, so if the rank of this coefficient matrix is n, right? So this is not a sufficient condition for the unique solution for this system of equations. The rank of the augmented matrix should also be n. Okay, so if you have rank of the coefficient matrix as n, and the rank of the augmented matrix is also n, right, then you will have a unique solution. Now what may happen is that the rank of the coefficient matrix, so this is the condition for unique solution. The condition is rank is same as the dimension, that is n, for your augmented matrix as well as for your coefficient matrix. And same is true for augmented matrix, right? Okay, now if the rank is less for the coefficient matrix, right? So basically if coefficient matrix, you say rank is less than n, or dimensionality of this matrix, and the rank of the augmented matrix, okay, is n, or basically if the rank of coefficient matrix is less than the rank of the augmented matrix, then there is no solution. So that's a condition of no solution. Now if the rank of the augmented matrix is same as that of the coefficient matrix, but it is less than n, then let's say how much is the rank. So let's say rank is equal to k for both coefficient and augmented matrix, and then the rank k such that k is less than n. Then there are infinitely many solutions for that. So what does it mean, right? So let's say if I have the rank of, so let's see diagrammatically. Okay, so infinite solutions. So that infinite solution is when this happens. Okay, Now, what does it mean? So it means that you do not have n linearly independent equations. You have less than n linearly independent equations in a dimension of n, right? So that means that you will not be able to find, you will be able to find multiple solutions for this, right? So this is equivalent to, let's say if I have a two-dimensional matrix, then it is equivalent to two lines which are kind of parallel to each other, right? So that's a no solution, sorry, that are coinciding over each other, right? So basically you can represent one solution overlying over the other solution, right? So in that case, it can pass through 0, it can pass through anywhere, right? Doesn't matter, right? If it passes through 0, that's a homogeneous. Okay, so let's say this is the two lines on one on top of each other, right? So in this case there are infinitely many solutions. That means that the rank of the matrix, augmenting matrix, and the coefficient matrix is same but less than n. So then in that case you can have what you call the k minus, so n minus k parameters, which you can insert it and you can have n minus k solutions there, right? So basically n minus k parameters can give you n minus k solutions. So that's infinite solutions, right? Okay, now if the rank of coefficient matrix is less than that of augmented matrix, then what might be happening is you might have two lines, or let's say in two-dimensional system, which may be parallel, right? So in this case there is no solution. Okay, so in this case there is no solution. Another thing that can happen is so another thing that can happen is a unique solution. So in that case of unique solution, the two lines basically can intersect, and that intersection would be the solution, right? So in a two-dimensional system this will happen. Now in a three-dimensional system, instead of a line we have to assume planes, right? So if you have two planes which are parallel to each other, so then there is no solution, right? Or the two planes are such that all the planes do not intersect at the same point, right? So they may intersect at different points. So in this case also there is no solution here, right? And in case they intersect at a common point, so basically if they intersect at another option that can happen is the planes can be having infinite many solutions like this. If they have a line common between the three planes, then also there is infinite solutions, right? Now for a unique solution, these planes are supposed to intersect at a point, so that will be the unique solution for a three-dimensional system, right? So for a system to have a unique solution, the rank of the both the matrices should be the same as the dimensionality. Then you will have a unique solution. Otherwise it is going to be either no solution, in which case the rank is of one matrix is is different from the other matrix less than n, right? So you will have no solution. Or you can have infinite solutions if basically the entire row disappears, or entire row is 0, or rather entire row is a algebraic sum of other rows in case of the augmented matrix, right? So then that would have what you call infinite solutions. So we are not going to go much deep into the solutions. Later on we are going to pick up, right? So let's look at some examples. Okay, so very simple example, let me look at. Okay, let's say I have 5x plus y is equal to 3 and 2x minus y equal to 4. So if I was to find the solution for this, okay, so there is a a well-defined procedure for that. So I can express this as an augmented matrix, right? Then I will do some row operations. So I can, what is allowed in row operations? I can take a row or I can take a row and I can basically subtract that from the other, right? Other row. So basically the I can do that to, so for example here, if I want to find the solution, what I'll have to do is I will take 5 1 3, then I will divide this by 5 and multiply by 2 and subtract the first row from the second one. So basically I do 2 into so I can do 2 into 5 by 2, so sorry, 2 by 5, sorry. I can do 1 by 5, so 2, so I can divide entire thing by 5, or I can leave it like that, so it doesn't matter. To 2/5 of the row. Okay, so 2/5 of the first row would be 2 minus 2, 0 here. Okay, and so here 2/5. Okay, so 2/5 is what I'm going to do. So 2 by 5, so 2 by 5 here, minus 1 minus 2 by 5. So that is going to be equal to minus 7 by 5, right? And here I would have 2 by 5. So basically I will have 6 by 5, right? 6 by 5 subtracted from 4, right? 25 was 20 minus 6, 20 minus 6, 14. So let me just quickly check it. I did the 2/5, multiplied everything by 2/5. So 2/5 of 5 is going to be 2, right? So I subtracted it from the second row, so that gives 0. 2/5 of 1 will be 2 by 5, and I have to subtract it from minus 1. That will be minus 7 by 5. And 2/5 of 3 would be 6 by 5 subtracted from 4. So 4 into 5 is 20 minus 6. Okay, 14 by 5. Okay, so here I have got, I can express now this again as minus 7 by 5x, or rather y, 7 by 5y is equal to minus 14 by 5. So when I do that, y is equal to 2. So I'm going to substitute this in the first equation and say 5x plus 2 equal to 3. So 5x is equal to 1, or x equal to 1 by 5. So let's see if this solution satisfies the first equation. So if I put x equal to 1 by 5, that will give 1, and then y is equal to 2, so basically that will give 1 plus 2, that will be equal to 3. So the first equation is satisfied. What about the second equation? 2 and 1 by 5, so that will be 2 by 5 plus 2 times of minus 1, minus 2. Minus 2 should be equal to, so hang on a second, 2 into 2 by 5 minus 2. So is something wrong? Did I solve it wrong? Hang on a second. Okay, so I was doing a mistake here. The mistake was, this was plus 14 by 5. Okay, so now I have minus 7 by 5y is equal to 14 by 5. So that means y is equal to minus 2. So now if I substitute that in the first equation, I will have x minus 2 by 5 is equal to 3 by 5, right? So x is going to be equal to 1. Okay, so the solution is x equal to 1 and y equal to minus 2. So let's substitute this back in the first equation. So if I substitute that as x equal to 1, so that will make 5 plus y equal to minus 2, so that will be minus 2, so that will be 3. Then x equal to 1, and then I do minus 1 into minus 2, so that will be equal to 4. Okay, so I have an equation like this. Now what did I do? I did what is called the Gauss elimination. So what you try to do in a Gauss elimination is you try to take a matrix and try to reduce that matrix into an upper triangular matrix, right, by doing certain row operations, right? So that form, okay, so that form of matrix is known as row echelon matrix, right? So let's see another example, which is going to be a example of a 3 by 3 matrix. Okay, let's do an example of a 3 by 3 matrix, and we do the row operations and trying to find out the values. So this was a 2-dimensional matrix. Let's put an example of a 3-dimensional matrix. So let's say this is going to be x plus y plus twice of z is equal to 9. Then you have got twice of x plus 4 times of y minus 3 times of z is equal to 1, and then you have 3 times of x plus 6 times of y minus 5 times of z is equal to 0. So now this system of equations can be written as 1 1 2 2 4 minus 3 and 3 6 minus 5, and then this will be written as 9 1 0. Okay, so this is my augmented matrix for this system. Now let's try to solve this. So I will take 3 times of the first row and subtract it from the bottom row. So that will leave 0 here, and that will leave 3 here, and that will be 6, and minus 6 is minus 11 here, and that will be 9 into 3 is 27, and subtract from that 0, so it will be minus 27. Correct. And then you have, I take the first row multiplied by 2 and subtract from the second row. I'm left with 0 here. Then I will do 2 minus this will be equal to 2 here. Then minus 3 and minus 4 is minus 7 here. And then you have got 18. Okay, 1 minus 18 is minus 17 here. And then you have 1 1 2 9. So now this is a row operation on the second and third row from the first row. Now what I'll do is I will proceed to reduce this 3 to 0. So what would I do? I will take I will multiply by 3 by 2, the top one, 3 by 2, and subtract it from this, so this will become 0. So minus 11 minus of 3 by 2, right? So 3 by 2, 21 by 2, 21 by 2. So it will be minus 21 by 2, isn't it? So that will be minus 11 plus 21 by 2. So that will be 22 minus 22 minus 21 plus 21. So that will be minus half, right? And then I will do 17 minus of minus 17 into 3 by 2, right? 17 3 is a 51 by 2, right? And that has to be subtracted from minus 27. So it will be minus 27 plus 51 by 2. Okay, so this will be minus 54, sorry, plus 51 by 2. Am I right? Okay, so that will be same as minus 3 by 2. Okay, so that will be same as minus 3 by 2 here. Okay, the other row is going to be 2 minus 7. I can leave like this if I want. Okay, 17, and the final row is 1 1 2 9. So what do I have here? I have the coefficient matrix reduced to a upper triangular matrix. Now I can do substitution, back substitution. So this will be minus half of z is equal to minus 3 by 2. So that means z is equal to 3. Now then the second row has got twice of y minus 7 times of z. So which will be 3 is equal to minus 17. Right? So twice of y, 21 minus 17. So that means that 21 minus 17 is going to be 4. Twice of y is equal to 4, or y is equal to 2. So now if I substitute this in the first equation, I have x plus 2 plus 2 times of z, which is 6, is equal to 9. Right? So x would be equal to 1. Right? So the solution of this system of equation is x equal to 1, y equal to 2, z equal to 3. So you see that this is referred to as Gauss elimination method. Right? In this Gauss elimination method, what did I do? I eliminated all the zeros in the lower triangle. So what do I mean by that? It means by that that matrix has got a diagonal elements. So all these elements are diagonal elements. So everything on the diagonal element and above is non-zero, and everything below is 0. So in this case, I'm able to find out the solution. Now let's see cases where there will be infinite solutions or no solutions, right? So okay, let's consider two-dimensional case to discuss this. Okay, so let's say I have got x plus y equal to 4. So I can put here x plus y equal to 4, and then I have got 3x plus 3y, 3x plus 3y equal to 6. So now what has happened is the coefficient matrix, okay, I can write this as 1 3 3 and then 4 and 6. Now if I follow the same Gauss elimination using elementary row operations, I can take 3 times of this equation, subtract from that. So I'll be left with 0 0 here, and I'll be left with 3 4s are 12 minus 6 over here and 4 over here. Now notice that the rank of the coefficient matrix is now 1. The rank of the augmented matrix is 2, right? And 1 is less than 2. The dimension of the system is 2. So now here you do not have any solution. So this is equivalent to 2 lines which are parallel to each other, right? So that's there. Now had this been exactly 3 times, okay, so had this been x plus y is equal to 4 and 3x plus 3y is equal to 12. Now in this case, if I did the same operations, right, if I did the same operations on this matrix, I would have 1 1 4 and I will have 0 0 0. Now notice that the rank of the coefficient matrix is same as the rank of augmented matrix, is same as 1 less than the dimension of the matrix, which is 2. Now this is equivalent to 2 lines which are going to be on top of each other, right? So there will be infinite solutions here and there will be no solutions here, right? So you understood that when do we have an infinite solution, when we have no solution, and when we have unique solution. Now in case of homogeneous equation, the the right hand side column is entirely 0. That means you can have all the variables to be 0. That is called the trivial solution. Or you can have what is called, so if the rank of the coefficient matrix is less than the dimension, then you will have many solutions. So for a homogeneous system of equation, there are only two possibilities. One is either you have a trivial solution which is all variables are 0, that satisfies that system of equations, or you can have infinitely many solutions when the rank of the coefficient matrix is less than the dimension of the matrix. Okay, so this is called Gauss elimination and back substitution. Now we could have reduced the matrix to just a diagonal matrix, isn't it? If we did the operation, if we can do zeros below the diagonal, we can do some operations for the rows above it, because if you have introduced a 0 here, and if you do algebraic sum, this 0 will not affect the 0 at the top, right? But then you can take a multiple of this, so multiple of this is multiplied by half and then subtract from here, right? So then this element would become 0. So you can basically eliminate the matrix to just be a diagonal matrix. So in that case, whatever remains on the right hand side would be the solution, right? So a Gauss elimination with a back substitution is one way where you reduce the coefficient matrix to upper triangular matrix, right? But then there is another way, is that you reduce the matrix into a diagonal matrix. Then the right hand side, which is B, is the solution of your system of equations, right? Okay, so that is your Gauss Jordan method, right? So you can do either of the method to solve a system of equations. Now apart from, so in that case the matrix which is just a diagonal matrix, right? Okay, so that will be reduced row echelon matrix. Okay, so a row echelon matrix would be upper triangular matrix. Reduced row echelon matrix would be just a diagonal remaining there, right? In that case you have directly the B as the solution. If all the elements on the diagonal are 1, then the B is the solution. So we will implement that in C so that we will be able to solve lots of equations just using a program, right? Now the next thing which I want to talk to you about was matrix manipulation, right? So it's not that it's just the system of equations where you see matrices. You might see matrices in other areas also. So for example, let's say there is a matrix A. Okay, so let me write down like this. There's a matrix A of order m cross n, and then there's a matrix B of order m cross n. Then you would be able to do A plus B, which will be element by element summation, right? So you will result in A plus B, which will be m cross n matrix, right? And the solution would be A11 plus plus B11, A12 plus B12, A13 plus B13, and so on up to A1n plus B1n. And then you have 21 plus B21, 22 plus B22, 23 plus B23, and so on up to 2n plus B2n, right? And similarly you can go up to an1 plus bn1, an2 plus bn2, an3 plus bn3, and up to ann plus bnn. So a member by member addition would be the addition of matrices. Okay, so now in this case you have to have the same dimensions. So if A is m cross n, B has to be m cross n to be able to do addition. Similarly, you will be able to do A minus B if their dimensions match. So that would be the difference. So you can have a sum of two matrices, you can have difference of two matrices. then you can also do a dot product. So dot product would be basically element by element multiplication of the two matrices, and which will be again m cross n. Okay, so this will be a dot product. So you have an addition, you have a subtraction, you have a dot product, but then you will have a cross product also. So if there is a matrix which is A m cross n, and then B is n cross O. Okay, so in this case these two dimensions have to match, right, to be able to multiply, and I'll show you how it multiplies. So this will result in A cross B, which will be of the dimension m cross O. Okay, so let's see. So addition and subtraction are straightforward. Okay, multiplication, which is a dot product, is also straightforward, and but the issue is your matrix multiplication, which is a cross product, right? So let's say if I take two matrices, let's say 1 1 2 2 1 3 2 2 7. Okay, so let's say this is a matrix 1, then the other matrix have to have the inner dimensions meeting. So this can be 2 cross 3. So this is a 3 cross 3. Then you can have a 2 cross 3, sorry, 3 cross 2, sorry. So 3 cross 2. So these inner dimensions have to match. So this can be 2, 4, 5, 6, 7, 1. So now you'll be able to multiply this matrix, and the result would be 3 cross 2. So how this will be done? So you are going to start with this multiplying with this. So that would be 2. Then this one would multiply with this. Okay, that will be 5, right? And then this one would be multiplying with this. That will be equal to 14, right? So now I'll do this with the right column also. Just 1 second. I will do the same with the right column also. I'll have 4 plus 6 plus 2. Then for the second row, I can have 2 into 2 is 2 plus 5 plus 21, right? And then you have got 8 plus 6 plus 3, and then you have got 4 plus 10 plus 49, right? And then you have got 8 plus 12 plus 7. Sorry for this. Hang on a second. Okay. Okay, so the answer would be 14 plus 5 is 19 plus 2 is 21. Then 4 plus 6 is 10 plus 2, 12. And then 5 plus 2, 7 plus 21 is 28. Then 8 plus 6 is 14 plus 3 is 17. Then 49, 59 plus 4 is 63. And then 8 plus 12 plus 7, right? So 8 plus 12 is 20, 27. So the answer is a 3 by 2 matrix. So let me verify that. 2 plus 5, 7. 7 plus 14, 21, right? Then 4 plus 6 plus 2, okay, 10, 12, right? Then you have got 2, 4 plus 5, 9 plus 21. I messed up. So this will be 4, right? Okay, so that will be 4 plus 5. 5, 4, 9 plus 21. So this would be 31, right? 2 into 2, 4, plus 5, 5 4, 9, 9 plus 21, 9 plus 21 is 30, right? And then you have got 4 to 8 plus 6 is 14, plus 3 is 17. Then you have got 4 plus 10 is 14, plus 49, 59 plus 49, 2 plus 2 is 4, plus 10, 14, 14 plus 49, 49, 59 plus 4 is 63. And then 2, 8 plus 12, 8 plus 12 is 20, plus 7, 27. So that's the right answer. Okay, so this would be called matrix multiplication, right? So we should be able to write program for all of these, right? So that's going to be our next effort, is to be able to write programs in C, so that I can give any size matrix and I should be able to find the solution. So let's say for matrix multiplication, let's start with, I can form my own system of equations and then try to solve it. Okay, so let's do that. Okay, so let's assume that there are going to be 4 variables. Okay, and these 4 variables are going to be w, x, y, and z. So let's say I give a value to w as 3, x as -1, y as 2, and z as 1. So I'm going to solve the problem in reverse, right? So I can write twice of w plus thrice of x plus y plus z is going to be equal to 6 minus 3, 3 plus 2, 5 plus 1, 6, correct? And then I would make another equation, let's say thrice of w plus 5 of x. So these are just randomly I'm writing equation, plus z, and that will be equal to 3 3 is 9, minus 5 is 4, 4 plus 4 is 8, plus 1 is 9, correct? And then I can have 5 times of w plus 3 times of x plus 7 times of y plus 2 times of z. So let's see what this will be. This will be 5 is 15 minus 3, that is 12, 12 plus 14, 26, plus 2, 28, correct? And then I am going to have let's say minus 2 plus 4x plus 5y plus z is equal to, so minus 2 would be minus 6 minus 4 minus 10 plus 10, and then you are left with 1. Okay, so I have formed my own system of equations which I want to solve on a computer to be able to get back my solution, right? So I'll use a Gauss elimination with something called pivoting. Okay, so what is pivoting is, see, you have to make sure that the diagonal elements are not going to go to 0. So if the diagonal elements go to 0, then you will not be able to find a solution, right? So what I'm going to do in logic is I am allowed to interchange the rows, right? So what I'll do is, for the first case, I will try in this column, I will try what is the maximum number. So the maximum number in the first column is 5. So I will replace the third equation with the first equation, right? I will interchange them, right? Now once I'm done with getting all the zeros below, then I will look at the second column. In the second column, I will start at the second position, and then in the second position we'll see which one is the highest, and that second equation I'll replace by that thing. So I will keep on finding out the maximum values, and I'll try to place these maximum values on the diagonals, right? So this is something called pivoting, right? You can also interchange columns But then if you interchange columns, you will have to do something on the right hand side by interchanging them. That will be called Gauss Seidel method, but then it is more complicated to do. So let me just go ahead and do the row operations so that I can reduce the system to a reduced row echelon matrix, which is just a diagonal matrix, and then I can find out directly the solution of this system of equations. Okay, so let's do that. Okay, so let's put this aside for now, and let's launch this. And here I am going to make a new project in C, and I will call this as empty project, and I'll call this as mat fun. So fun with matrices, and say okay. Okay, so once I'm done with this, I'm going to write. Now I've got two choices. Okay, one is the matrix can be created in a stack. Other is that the matrix can also be created in a heap. Okay, so now the heap comes under what is known as a garbage collector. Okay, so if you follow my other playlist, you will know what is a stack and what is a heap and what is a garbage collector. And I would encourage you to go through the session in the playlist which is called programming in C. Okay, so before you can do this, so C and this mathematics will go hand in hand as we go forward. Then there is another playlist which is going on, which is called digital image processing. So there also I'm going to apply all the things which we learn in C and which we learn in mathematics to image processing. Same thing I'll do with the signal processing. So all the subjects are supposed to go hand in hand. Okay, so here let's say I'm going to create another file here. Add a item, new item. Okay, and I will add a C file here called matrix manipulation. Matrix manip. Okay, dot C. Okay, so let's create that. Okay, let me make sure I'm recording. Okay, so now I am going to write here all the functions for adding two matrices, subtracting matrices, multiplying the dot product, the multiplication, Gauss elimination. So I'm going to do all that. I'm going to create another C file which I'll call main program, right? So I will call main app dot C. So I will call these functions from this main app, right? Okay, the third thing which I want to have is a header file. So I'll make a header file for your matrix manip. So it will be the same name, matrix manip. Okay, so spelling is the same, right? So .h. Okay, so now I have three sets of files. I'm going to write all my C functions here. So first thing first is in C, if you have to follow the sessions in C, because you don't only have to learn mathematics, you should also be able to apply it. So as I was saying, that there are two forms of storage. One is called a stack, and on a stack the storage is contiguous in the sense that it is in the sequence, right? The memory blocks, the memory addresses are in sequence, right? And this is using the stack of the processor. So the stack is limited. So if you have big matrices, right, then it will just run out of memory, right? You have to have so much of RAM. So that's why it's not a good idea to deal with large matrices in a stack. But then there is something called heap, where you can have more area, right? But the issue there is that heap is not secure. in the sense that heap is visible to other threads and processes in a computer, right? So when that happens, some other thread or some other task would overwrite or may corrupt your memory, or may modify it in the way you don't want it. Okay, so that's why there is a problem of uh, security. And second thing is that it is not contiguously stored, so you may run into what is called memory fragmentation. So you can use matrices can be stored on stack, and matrices can also be stored on as a memory block on heap. But when you do it on a heap, you will be responsible for clearing the memory. But then if you are jumping between functions calls, right, then you might have to do a static, which is another problem, right? So heap matrix management on heap is going to be very complicated, and it will be prone to what is called memory leakages. So if you do not free the memory gets blocked till the main thread of the program is exited. So I tried both of them, and stack was more secure. It didn't give so much error, so I'm going to stick to creating things on stack. So that means that I will be dealing with matrix rather than allocating memory using malloc. Okay, so you can try using malloc also, and if you are not able to understand what I'm talking about, you can refer to uh, another playlist on programming languages, and the first session on that is about C language. So in this case, I am going to have certain header files, stdio.h hash include stdlib.h. Then I can have stdbull include std hash include spelling is wrong, hash include std bool.h. Okay, and std and math.h hash include, though we may not be using anything from math.h for now, but we never know. Okay, so that's there. So I am going to write first the sum. So in the main program, I am going to create two matrices. Okay, so here in the main program, I have to just do, I can copy the whole stuff if you want. So what I'll do is the following. I'll copy the entire thing. Copy. May not be the good way of doing it, but I don't want to see errors. Okay, and then user defined header file, which is going to be include, right, and then user defined usually comes under this, and there is only one header, so it just shows up like that. Okay, so we are all set with this. And then you have got the main entry point, which is going to receive void, and it's going to make the function calls. Okay, so let's just create a matrix. So let's say that matrix is A1, which has two dimensions, which is, let's say, 3 by 3. We will expand, we will change this to do other, other examples. So here this can be linearly allocated. So I can just say 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are 9 elements, 3 cross 3 elements, right? And internally the storage is all linear like this. So it is not a 3 cross 3 matrix, it's rather a vector, right? So that's how it is. So let's take the other one, which is A2. It's another matrix which is 3 by 3. Now these dimensions are supposed to match, otherwise the addition will not take place, right? And here, sorry, here I'm going to put 3, 2, 5, any random number, comma 7, comma 2, comma 8, right, comma 2, comma 5, 2, comma 5, comma 2. Let's see how many I have. 3, 2, 5, 7, 2, 8, and 2, 5, 2. So they look like 9 of them, right? So fine. So we have created two matrices. Now we are supposed to add them. So I am going to receive the addition in something called another matrix, which I will call as sum. Now the thing is that I could have written sum as this. Okay, so sometimes this might goof up. Okay, so what happens is if you go as a pointer notation versus a matrix notation, it might goof up sometimes. So I'll just reduce it to a row vector where I'm just supposed to receive the sum. Okay, so that's straightforward. Now I'm going to write the sum. Okay, so I have to call sum. So let's say I'm going to call this sum, which is going to return void. So over here I'm going to write void, and I'm going to call this as sum, capital sum, right? And I can receive, so I'm going to return the results in a double, pointer to a double, which is your matrix, which is called sum. So I'm going to receive the sum over here. Then I'm also going to receive a pointer to your matrix, which is called double A1, right? So these names can be same, doesn't matter. Then I'm going to receive double, and here I'm going to say I'm going to receive A2, correct? And then I'm going to receive the dimensions. Okay, I can say int m, so this is number of rows, and int n, which is number of columns. And let's say if I want to display it, I'm going to receive a boolean which says echo, or ECH, or echo. So I'm going to echo this. So this is what I'm going to write. Okay, so now that means that if I have to call it, I will have to call up to here. It's a copy and paste it over here. So I am calling, so I'm calling sum, where I'll return the results, and I'm passing the pointer to A1. So basically a matrix name is a pointer. Okay, and here I'm going to pass 3. So the number of rows is 3, number of columns is also 3, and then I want to display it, so I will return here true, and that's my function call. Now this function has to be declared, right? So I'll declare in the header file. So I'll take this entire thing, say copy, go to the header, say paste. Okay, and this is a prototype, so I need not mention the names here. I have to just mention the types, right? So very quickly let me do that. Okay, so this is my prototype declaration, which will be included by this header file. Okay, so let's write what's inside here. So if echo, if there is a echo, then I would just say printf, and here I'm going to just say a new line character. So I'm going to output the results with the new line. Then I'm going to do two for loops. One is for the rows, which is the outer for loop. So I can say for, I can write here int I equal to 0, I less than m, so, and then I plus plus, correct? Okay, so having said that, now I'm going to deal with the columns. So I will need another for loop. I'll say for int j equal to 0, j less than n, which is number of columns, and j plus plus. And here I am going to have this. Okay, so now what am I going to do inside? Okay, I am going to, okay, and in between this, okay, I'll add this again. This is only for the display purposes. Okay, just to separate, the rows. I'll have a new line feed. Okay, so here I'm going to use pointer notation. So I want to store the results in a pointer which in the sum. Okay, and here I want to go, so I want to go, so wait, so I want to go to this pointer plus I times of m plus j, right? Oh, and just to be clear, this is what it's going to do. Okay, so this should be equal to the summation control C, control V. So this will be for A1, same indexes, plus A2, right? And that's it. And if there is an echo, then I am going to print the solution. So I'm going to say printf %f, and then a tab, and here I am going to put this thing, control C, control V, and that. Okay, so I'm going to sum the two matrices, right? Okay, so this is my sum. Okay, so let's try this. So let's try to run this, because I have already called it over here. Save the sum results in sum a1, n2, 3, right? So let's go here and say build solution. Okay, don't worry about this. Okay, so that warning is of no consequence. And then I'm going to debug this. Okay, so this is my summation. So what this is 3 plus 1 is 4, 2 plus 2 is 4, then 3 plus 5 is 8, and then the second row, 4 plus 7 is 11, 5 plus 2 is 7, 6 plus 8 is 14, 7 plus 2 is 9, that is the third row, 8 plus 5 is 13, 9 plus 2 is 11. So that's the sum, right? Okay, so that's very straightforward. Now what I can do is I can convert this into a difference. So I can go here and add another matrix for the result, which has again the 9 members only, right? And here I am going to say diff, and here I'm going to receive the results in diff, comma a1, comma a2, comma 3, comma 3, comma true. Okay, so that would be the difference. Now I have to, if before I call this function, I'll have to create it. One quick way is I'm just going to modify this. I'm going to say control C, I'll say control V, and this one I'll call capital diff, Okay, and this one I'm going to receive is called diff, and the remaining thing is this is diff, and this would be a minus sign here. Sorry, and this would be diff. So I have very quickly written the difference, right? And I have to add a prototype for this. So all I have to do is I'll just copy this, Control C, and I'm going to paste it over here, Control V, and then I don't need these, okay, because it's a prototype, so you need not have a instance for this, though it's not going to hurt if you leave it. Okay, so diff is ready, and it is going to display its prototype is ready, and I can just call it over here. It's already called over here, and I'm just going to run it. So build solution, and I'm going to say debug, start without debugging. Okay, so at the top you have the sum. Let's verify the difference. So 1 minus 3 is minus 2, 2 minus 2 is 0, 3 minus 5 is minus 2, then the second row is 4 minus 7 is minus 3, then 5 minus 2 is 3, and 6 minus 8 is minus 2, and then 7 minus 2 is 5, that's the third row, 8 minus 5 is 3, 9 minus 2 is 7. So difference works. Okay, now very quickly I can do this as a multiply, or I will call this as a dot. So I will call this double as dot, and same number of elements I'm going to receive, right? And I'm going to call this as dot product. So I'm going to go here and say this as a dot, dot, and this I will call as dot, dot, and the remaining things remain the same. All I have to do is go over here, just copy this out, and paste it here and call this one as dot, and I'm going to receive a dot here, and I'm going to store this in dot, and this will be a multiplication. So unary operators have precedence, so we really doesn't matter if you put it in a bracket, it will still give you the results. Okay, so we are done with the dot multiplication. So I'm just going to create a prototype of this. So copy this into the header file, right, and I'll remove the unnecessary stuff here. And then I put a semicolon. So this is a prototype. So I have a function, I have a prototype, and I'm calling it. Okay, so just build it and just run it. Okay, that's the result. So let's see, 3 into 1 is 3, 2 into 2 is 4, 5 into 3 is 15, that's the first row, 4 into 7, 28, that's over here, 5 into 2 is 10, then 8 into 6 is 48, 7 into 2 is 14, then 8 into 5 is 40, and 9 into 2 is 18. So this is the dot product. Now let's do the multiplication, that is the matrix multiplication. Okay, so I'm going to do very quickly this matrix multiplication. Okay, so here what's going to happen is I'm going to create a new output, double, and call it as multiply, and it is going to have again 9 members, 3 cross 3, right? So you can put 4 cross 2, 2 cross 4, right? for multiplication, that will be 8. So it's 3 cross 3. So let's just write this as MUL, and it is going to receive the results in MUL, right? And then I'm going to pass it A1, I'm going to pass A2, then I'm going to pass M cross N cross O, if you remember. So M is 3, N is 3, and O is also 3, right? And then I want to display it, so true, and that's it. Okay, so this is how I'm going to call it. So let's write a function over here which would be a repetition of this, slightly modified. So let me just copy and modify it. Okay, so I'm just gonna copy and modify this M and O pull. Okay, so just copy this, Control C, Control V. So in this case I will call this as MUL. It is going to receive the results in MUL, and it's going to receive A1, A2, then it's also going to receive int O, not 0, O, and a boolean. Okay, so first thing, if you remember, we were to do a column, a row multiplied by a column, right? And then add it up, right? So what to add it up, I am going to introduce here a double. So double, double, and I'll call this as sum, and I'll give it the initial value of 0. Correct? Then I am going to run the outermost loop for the rows, which is going to go from 0 to m, correct? And then I am going to have j, and the j would be running from 0 to o. Okay, and then let me just remove this. Okay, over here I am going to store the results for I cross j into sum equal to 0, correct? And then I'm going to run another for loop for k from 1 to n for the columns, right? So for every column I'm going to do this operation. For is that right? Yeah, yeah. For int, so you have ij, now let's say k is equal to 0, k is less than m cross n cross o, so j is for o. Trying to understand this. Okay, so m cross n, n is common between the two matrices, the inner number, so it will be n. Okay, so k less than n, k plus plus, and then I am going to, okay, right here sum is, so in this case it will be a vector notation, no, it will be sum. Sum is equal to, let's write this out in a vector notation. Okay, so I am going to receive something, so it will be sum plus, sum is equal to sum plus multiplication of the two numbers. So this will be the width is is going to be n, right? So it will be a1 plus n times of k, n times of I. Okay, so this is a1, right? So n times of I, so I represents the row, plus k, so that would represent the element. Okay, fine. Okay, so I am going to put the bracket around this. Okay, and then that is to be multiplied with uh, something. So to differentiate, I'll just put this one. So I will put the pointer inside. Okay, and that pointer would be a2 plus n times of O times of k. Just 1 second. Oh, let me try to understand this. So this is wrong. This has to be O. Okay, so the second matrix has a dimension O for the number of columns, right? O times of k, isn't it? O times of k, and O times of k. K is updating, right, in the inner loop. And this you are going to do for j times, right? Okay, so I think this is correct, but I'll keep this in a, so I'll keep this in its brackets, right? And this one is it in its own brackets. Okay, so at the end I will assign this sum to the output. So in this case the output is going to be inside multiply plus, okay, and this will be m times of, hang on a second, so total number of columns m rows n columns. Okay, okay, m cross n, m cross n. Okay, so m, so this is really the width. Total width is going to be O, right? M cross O. Right. So let's try this. So the total width will be O times of I, right, plus j. I is going from 1 to m, right? Yeah, so this is correct. Should be equal to sum. So we'll try this out. If it doesn't work, then we will know. And here I am going to display the same stuff. Okay, so we might have to troubleshoot because I'm not very sure on the indices. According to me, the resulting matrix is going to be m cross n, right? So that's fine. Let's see. We'll do that. So this is what we want to display. Okay, so we are done with this. Let's run this. Okay, so let's create a prototype. Let's create a prototype of this. Control C, and this is a matrix multiplication. Control V. Okay, so we will try this with a rectangular matrix rather than with a square matrix to make sure our dimensions are right. Okay, so once we do this, we are calling it over here, and this is the function which is being called, right? So first of all, O times of k plus j, correct? This is n times of I plus k. This has to be O times, correct? So let's just run this. Build solution. Okay, and debug. Start without debugging. Hope for the best. So there's the result. Okay, so we have got 23, 21, 27, 59, 48, 72, 895, 75, and 117. So to check this, let's go back to our input. Okay, and so here a first row and first column, so it will be 3 plus 5 to the 10, that will be 13 plus 7, right? 3 to 5, right? 7 to the 14, 3 plus 14 is 17, and then this 3 will go with 2, 6, 17 plus 6 is 23, correct? And then let's look at the second column. Second column will be 2 plus the 2 plus 2 into, so it will be 1, and we are looking at second column, right? So that will be 2, and this will be 4, 6, and then 3 5s are 15 plus 6 is 21. So that's your 21 here. Let's look at another one, which is going to be 1 into 5 is 5 plus 2 into 8 is 16. 16 plus 5 is 21 plus 3 into 2 is 6. 21 plus 6 is 27. So 23, 21, 27. That's the first row. We'll verify the second one. Okay, the second one will be 4 into 3, 12. 12 plus 5 into 7, 35. 12 plus 35 is 45, 47. 47, and 6 into 2, 12. 47 plus 12, 57 to 59. So the first one is 59 over here. And then let's look at the second one. So this will be 4 into 2 is 8. 8 plus 5 into 10 is 10, which is 18, plus 6 into 5 is 30. 18 plus 30 is 48. So that's 48. And let's look at the last one is 4 into 5 is 20. 5 into 8 is 40. So that is 60. 6 into 2 is 12. 60 plus 12 is 72. So that's 72. And then let's look at the last one, which is 7 into 3 is 21. 8 into 7, 56. 21 plus 56, 66, 76, 77. And 9 into 2 is 18. 77, 87, 97, 95. So the answer is 95 here. Now let's look at the second one. 7 into 2 is 14. 8 into 2 is 16. 16 plus 14 is 30. 9 into 5. 45 plus 30. 75. Right? And let's look at the last one. 7 into 5 is 35. 8 into 8 is 64. 64, 74, 84, 94 or 5. 99. And 9 into 2 is 18. 99 plus 18 is 117. So that's the matrix multiplication. Now let's say if I change this into 2 and this into 4, so there are 2 rows and 4 columns, then I have just this, correct? And similarly I have to match the dimensions here, 2 into 4. Okay, so that would be that. Okay, and the results would be in 8. And similarly over here 8. There are 8 elements only. Dot products will be 8. And then here it will be 4, isn't it? You have got 2 into, so let's do 2 into 4. Then I need another matrix, is it? Or I can modify this one. Okay, so for now I'll not do multiplication. Okay, done. So I'm just going to check first 3. So in this case I will be calling 2 as the number of rows, 4 as the column. 2 and 4 and 2 and 4. Okay, so now if I call this, say, will solution, unless I goof up, it should be nice and clean. Okay, so you have got 4 plus 4 plus 8 and then 11, and then this one is going to be 10. Huh? 5 plus 2. Hang on. What happened here? Okay. This should be 7, right? This is 6 plus 8. This should be 14. This should be... So what went wrong here? This should be 9. 8 plus 5. So the second row is not matching up. Why is that? Okay, I'm going to put you on a pause till I figure this out. Okay, so with the vector notation, you have to be careful. Okay, so this would be the width of the matrix. So this should be the width, means the number of columns. The columns should be n. Earlier I typed them as m. So this will be all n's, right? So when it was 3, it didn't really matter, but when it was 2 cross 4, then it really matters. So now instead of this being, this should be the width of the matrix, right? So this is n right now. So number of columns is the width of the matrix, right? Width of this row. So I have to change all the m's to n's. Similarly for this difference also, similarly for this dot product also. So now let's run this again. Okay, so debug. So let's build it. Build solution, debug, start without debugging. Okay, so now let's check this. 3 plus 1 is, okay, 3 plus 1 is 4, and 2 plus 2 is 4, 3 plus 5 is 8, 7 plus 4 is 11, 5 plus 2 is 7, 6 plus 8 is 14, 7 plus 2 is 9, and 8 plus 5 is 13. And let's look at the difference. 1 minus 3 is minus 2, 2 minus 2 is 0, 3 minus 5 is minus 2, and 4 minus 7 is minus 3, 5 minus 2 is 3, 6 minus 8 is minus 2, 7 minus 2 is 5, and 8 minus 5 is 3. Correct? And multiplication, 3, 4, and 15, and 28, and 10, and 48, and 14, and 40. So this is fine. So now this is correct. Now let's look at multiplication. So in this case of multiplication, let's disable this one. Okay, so I'm not going to call the dots and the crosses. I'm going to call the multiply. So I'm not going to call these because the dimensions won't match, right? I'm going to call this one. So I'm going to make A as 2 cross 4 and A1, and this is going to be 4 cross 2. So as both are 8, so it really doesn't matter, but then the result is going to be in 4. Okay, and so here I'm going to pass on 2 cross 4 cross 2, right? So 4 is common in between, and then 2. Okay, so let's go ahead and first check if in multiplication we haven't goofed up. So in multiplication, I am going to receive I, this is for the rows, which has a width of m for the first matrix, and then you have got j, which is the width of the second matrix, right? And k, which is the height of the second matrix, right? So I'm saying sum, and then sum is equal to a1, where it is going 1, which is I, and that is going k, and the width are n across here, and here I am going width is O, I'm going k, and I'm looking at the j, right? And then I'm looking at width of the first one, so 3 cross, so this will be, the width is going to be O, and j. So this looks okay to me. Let's see what's the result. Okay, so I'm going to say build solution. So if I don't goof up, I'll be lucky. Okay, so let's look at this number: 27, 60, 75, and 148. So let's verify that. Okay, so now the first row with the first column. So 1 with 3, that is 3. 2 with 5, that is 10, 13. Then 3 with 2, that is 6. 13 plus 6 is 19. Then 4 with 2, that is 8. 19 plus 8 is 27. So that's 27. Let's look at the second one. So 1 with 2 is 2. 2 with 7 is 14 plus 2 is 16. 3 with 8. 8 is 24. 16 plus 24 is 40. Then 4 with 5, 20. Uh, what are we looking at? 1 with 2, that is 2. 2 with 7, 14 plus 2, 16. 3 with 8, 16 plus 24 is 40. And then 5 over 20, 40 plus 20 is 60. So that's 60. Let's look at the second one. 5 with 3, 15. 6 with 5, 30. That is 45. 7 with 2, 14. 45 plus 14 is 45. 55 plus 4 is 59. And 8 with 2, that is 16. 59 plus 69 plus 5, 75. So that's 75. Let's look at the last one. 5 with 2 is 10. 6 with 7 is 42. That is 52. 7 with 8 is 56. 56 plus 52 is going to be 110. 56 plus 52 is 108. And 5 8s are 40. 108 plus 40 is 148. So that's your matrix multiplication here, right? So that matrix multiplication works. So now, having done this, let's put it back to 3 3 3, and then comma 9 and 3 3 comma 2. Let's put this back to 9. So I'm doing a 3 by 3 matrix, right? And I'm also multiplying 3 by 3. And here also I'm a matrix multiplication of 3 cross 3 cross 3. So that will be 3 cross 3, which will be 9. And this will be 3 cross 3. Okay, so everything looks okay here up till now. 3 cross 3. And this one is going to be 3 cross 3. And here also it will be 3 cross 3 cross 3. Okay, so I'm going to run this again. Will solution. Debug, start debugging. So let me just verify this one. 7 plus 4 is 11, 5 plus 2 is 7, 6 plus 8 is 14. So that looks okay. So everything looks okay here. Okay, so now this is matrix multiplication is fine. Okay, so now let's do one more thing, is solve a system of equations. So let's say I'm going to write a Gauss Jordan method. Okay, so in Gauss Jordan method, okay, it will be slightly involving, but I am going to do it anyways. Okay, so if I mess up here, I'll be in deep trouble. Okay, let's start writing. Void Gauss elimination. Right, and here I'm going to receive a augmented matrix double. I'm going to call this as augmented matrix. Then I'm going to receive a coefficient matrix which will be double, and this will be called coefficient. Right, then I am going to receive the RHS which will be a double, and that would be a RHS. And then I'm going to have in X as number of equations, in Y as number of variables, and then I'm going to have Boolean for the printing purposes. Okay, so now here I can start writing. So what does it say? Unnamed prototype. I'm writing. Oh, because I have to give it equal. That's why it is crying. Okay, so now I'm ready to write. So first of all, I'm going to just put a printf. 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 And new line character. Done. Okay, so now first of all I'm going to prepare an augmented matrix. So I'm going to take the two matrices, coefficient and RHS, and put them together. So for int I is equal to 0, I less than your number of equations, this is x, and then y plus plus, correct? And so this is for the columns. See, this is for the rows, and then for the columns I'm going to say for int j equal to 0, j less than y, j plus plus, correct? And then I'm going to say augmented. So I'm going to say augmented matrix plus, okay, I'm going to say y plus 1, because now the columns has increased by 1, right? Y plus 1 times of I, so that will be the width of the matrix, plus j, that will be the column going across the column, and I'm going to fill it with the coefficient matrix, right? So I'm going to fill it this with the coefficient matrix, okay, plus y into I, okay, plus j. So I have filled the coefficient matrix here, and then I have to fill the B. Okay, so here let's first write down what I'm going to send. Okay, first of all, let me write the prototype, otherwise it's going to complain. So I'm going to take this prototype, put it in the header file, right? And here I am just going to do this. I don't need this extra naming. Okay, so this is number of equations, and this is number of variables, and this is whether I want to echo the result. Okay, so we are done with this. So this is going to be included in the main, and I'll be able to write this. So for the main, how? Why I'm doing opposite? This should be inside the main, and this should be inside the matrix. I hate this. How did I goof this up? I'm writing the main in this and calling it. Control X. Oh my god. Control V. And I'm going to take all these equations. Control X. This is under matrix multiplication. Control V. And here, so why did I get confused in first place? Okay. Control X. It's kind of strange. Control V. Okay. So before even I go and do this, let's run our previous programs so that make sure it's not broken. Sometimes I do stupidity. Okay, this is matrix manipulation.c. This is its header file. This guy would not be there, right? So save it. This is main program from where I'm calling. Everything looks okay. Let's build solution. This is kind of strange. If it works, it is use stranger. Okay, it does work. It didn't break. Okay. Anyways, so here I was working with Gauss elimination method. Right, so its prototype is going to be generated over here. Okay, so remember, if you remember, I created this equation, right? So 2, 3, 1, 1. So let me create this matrices here. So let me just create this matrices here. So I will call this as double and call this as A3, and this is a 4 by 4 matrix, right? And this one I'm going to assign as a sequential. Okay, so the sequence will be 2, 3, 1, 1, right? 2, 3, 1, 1, comma 3, 5, 2, 1, 3, 5, 2, 1, comma 5, 3, 7, 2, 5, 3, 7, 2, comma minus 2, 4, 5, 1, minus 2, 4, 5, 1. Okay, so this is your 4 by 4 matrix. Let's verify this. 2, 3, 1, 1, 3, 5, 2, 1, 5, 3, 7, 2, minus 2, 4, 5, 1. Okay, so that's fine. And then you have 6, 9, 28, 1. Okay, so then I would do a double, which is the RHS, right? So I'll call this as B. This is a 4 cross 1, correct? And this one would be 6, 9, 28, 1. 6, 9, 28, sorry, 28, 1. Correct? Okay. So now I'm going to call this Gauss elimination. And I want to keep the results in augmented, right? So how many things do I need? I need 4 cross 5, that is 20. So I'll create another, so I will call this as double, and the results goes into augmented 20, correct? And here I'm going to call Gauss elimination. So let me go to this one and copy this out. This, Control C. Everything is okay over here. Correct. Control V. Okay, so let's fill this. So I'm going to return the results in augment. I'm going to pass on the coefficient matrix, which is A3. So this will be A3. Then I will pass on the right hand side in the matrix B. Then I'm going to have number of equations as 4 and number of variables as 4, and then I'm going to echo this as true. Okay, so that's how I'll call the Gauss elimination method. Right, and let's write this out here. Now I don't need anything. Let's just write this out here. This is going to be tedious. I'll tell you what I'm doing, but it's not going to be simple. Okay, so I filled with the coefficient matrix, correct? And then I have to add the last one. The last one would be augmented matrix plus y plus 1. So y plus 1, that is number of variables plus 1, that is the width of the total augmented matrix, times of I, right? And then you are looking at the last element, which is going to be y. Okay, should be equal to the contents of RHS plus I. Now I'm going to use similar algorithm for inverting a matrix also. So in that case, there will be an identity matrix here. Okay, so that I'm not going to talk right now, but later on I'm going to do it. Okay, so by the end of this, I would have an augmented matrix here. Then I'm going to basically run into, okay, I'm going to run a loop for the equations. So I am going to have how many equations? I'm going to have y equations, which will be kept track by k. K less than, is that so? K less than y, actually it should be x, right? But they are going to be same, right? So it should be x actually. This is going to keep the track of equations, right? Okay, but anyways, it's going to be a square matrix, so doesn't matter. K plus plus, and then something with the for. Then here I am going to compare. Okay, I'm going to compare the diagonal element. I want the diagonal element to be maximum, right? So I will run j from k plus 1 to the number of equations, right? Okay, let me put here y. I'm kind of confused, but later we will see what happens. And here, so I'm going to create a temp index. The temp index is k. Okay, so now I am going to compare. So I'm going to say for int j is running from int j is running from k plus 1. So it's going to look at the next elements, and j will be less than the total number of equations, which is x and j plus plus, right? And what am I going to do? So this temp has to be declared at the top as an integer, isn't it? Okay, so I will declare here int temp, right? Then also I am going to have a swap, which will be a double for swapping the two rows, right? Okay, so now here I am going to say if something, so that something would be magnitude, not the sign. So I will say fabs of something is less than, fabs of something is less than fabs of something, correct? And what this fab would be, augmented matrix element, correct? So that will be the augmented matrix element AUG plus, here it will be y plus 1, that is the width, times of temp, right? So temp is k to start with, plus k. Okay, make sense? Okay, then this will also be augmented matrix plus the width, here what happened to this, into j plus k. This is going to be y plus 1. So why doesn't it give highlight? So this is if, this is with the fabs, this is with the augmentation, this is with the y, this is with the fab, so that's fine. So if this happens, I am going to change temp equal to j. So I am finding out what is the highest element, correct? So once I have the highest element at the end of the loop, okay, I'm gonna swap. So I'm gonna swap the two rows. So this will be straightforward for int j equal to 0 and then j less than equal to y, which is number of variables, less than equal to y, j plus plus. Okay, so now I'm going to swap it. Isn't that clear? So I'm swapping it. So I will say swap is equal to the contents of augmented matrix plus the width, which is y plus 1, y plus 1 times of okay, so whatever is stored in the temp is the highest one, so I have to exchange for the kth value, right? So this will be k plus for all j entries. Swap is equal to this. Why would there be a problem now? No. So it will be okay, and then this value can be assigned the temp value. So in this case, this is equal to this temp, isn't it? Okay, then whatever is the temp, will be assigned swap. Okay, so what did I do? I assigned the kth to swap, then temp to kth, and then swap to temp. So now I have exchanged the the rows. Okay, now here I am going to divide the leading element by itself, and then the rest of the row by itself, right, by it. So I'm going to say swap is going to be equal to the leading element. So the leading element is going to be the content of the augmented matrix plus y plus 1, which is the width of the matrix, times of k plus k. So that's a diagonal element, right? So that diagonal element is in swap. And then I am going to divide the entire row by that. So kth row will get entirely divided by swap. So I'll say for int j equal to 0, j less than equal to y, j plus plus. Correct? So I'm going to normalize this with the diagonal element for the kth row. Okay, so for the kth row, this will be y plus 1 times of kth row plus all the elements, which is j, should be equal to, okay, same thing divided by swap. Same thing divided by SWP. Okay, so now I have divided the kth row with the leading element, so I have normalized it. So now I have to just reduce the non-diagonal elements to 0, isn't it? And that will complete my Gauss elimination method. So for that I will do for int j equal to 0, j less than x, and j plus plus. Okay, so I'm running across all the rows. Then if I say if j not equal to k, so non-diagonal elements, if j not equal to k, then do something. So that something would be so I will take the element in that column, right, as a multiplying factor. Swap is equal to augmented plus y plus 1 times of j plus k times of j plus k for the kth column. So that goes as that. Okay, something here not equal to. Okay, so next is I am going to run it across the entire columns in that row. So I'll say for int L equal to 0, L less than equal to Y, right? That is number of variables, plus L plus 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 plus, and then I am going to do the subtraction, okay, on J and L. Okay, so I'm going to say something which is augmented matrix plus Y plus 1 times of J plus L. Okay, so I am taking all the elements of that row, and it's going to be equal to the first element, the same element from which I will subtract the multiple. The same element from which I'm going to subtract SWP times of the diagonal element. SWP is the okay, understood. SWP times of something, and that something is going to be the entire row, which will be the augmented matrix plus the width of the matrix, which is Y plus 1 times of J times of K plus L plus L. Okay, let's check this one. Okay, to me it looks okay. So now once I come out of this, it would have solved it would have reduced the coefficient matrix part of the augmented matrix to be a identity matrix, and the result would be in the rightmost column. Okay, so let's print that augmented matrix. So if echo is there, I have to just go for int I equal to 0, I less than equal to Y. So this is number of I keeps a track of number of rows, right? So this would be x, and then say I plus plus, right? And then I am going to say for J, so this will be for the column, for int J equal to 0, J less than equal to Y, number of variables, J plus plus, and here I'm going to write printf percentage, so printf %f tab, and I should write here the augmented matrix, right? So pointer would be augmented matrix plus Y plus 1 times of I plus J. So that would be the printf, and I should insert here a new line character, printf, and here I should enter a new line character. So I am done with the Gauss elimination method here. Okay, so I'm expecting that when I run it, I'm going to get 3, -1, and 2 and 1, and an identity matrix. Okay, so let's go to main. It's running this. This is the matrix, this is the input B, which is RHS, this is true. This is the header have it, and this is there. So let's just call this. So if everything goes okay, and let's run debug. Okay, so let's look at the final. So why is it not inserting a print? So println. So I want to just separate them out. So let's go here. So I should put here one more printf, print new line character. And if I do this under K, so under K I should put here a new line character, right? K is keeping track of all the equations, isn't it? Yeah, so under K I will put a new line character. So over here maybe. So no, this is separate issue, right? So once it has run completely, I should keep it outside, isn't it? Control X. This should be way outside after this, isn't it? Yeah, now it should be okay. Build solution. Debug, start debugging. Okay. Okay, so I'm printing the final results here. I should still want one more new line character between the solution, isn't it? Okay, or I can do one thing. Let's switch this off. I just don't want... No. I just want to insert one more new line character, right? Before printing it out. So I should put here... Okay, before this, after this for loop. So I say printf new line. Okay, so let's run this. Build solution. Failed. Oh, printf. Okay, build solution. Succeeded. Start without debugging. Results. Okay, so look at this 4x4 matrix. This has diagonal elements as 1 and off diagonal elements as 0. So don't worry about this minus sign because this is machine precision, right? So all diagonal elements are 1 and the answer is 3 minus 1, 2 and 1. So if I go to here, 3 minus 1, 2 and 1. So 3 minus 1, 2 and 1. So that's my answer from Gauss elimination. And this is how I created the system, right? So to have answer as 3 minus 1, 2 and 1. So this completes, okay, a little exercise on, solving a system of equations. Thanks a lot. Thank you.